Hello everyone, I am Professor Anish Vora and I welcome you all in this video lecture. In this video lecture, we will study logic circuit implementation using only NAND gates. Before we start actual implementation using NAND gate, let us revise NAND gate. We have a symbol for NAND gate. We have two inputs, A and B, and output, that is Y. We can write Boolean expression for the NAND gate, that is Y is equal to A dot B bar. We know the characteristic for the NAND gate is that is AND gate, and output of the AND gate is inverted. So we write A dot B, that is a Boolean expression for the AND gate, and we take a bar complements, that is for the NAND gate. One thing should be very clear, that whatever input we are giving to the NAND gate, here we have given A and B, so we get at the output that is A dot B bar. But instead, if we give A bar B bar as an input, then we get A bar dot B bar and whole bar. We will be using De Morgan's theorem also. So let us revise first theorem of the De Morgan. De Morgan's first theorem says that the complements of a sum equals the product of complements. So complement of a sum, that is equal to product of complements. So here we have complement of a sum, and that is equal to product. Here we have a product, A bar dot B bar, product of complements. So this should be very clear, because while using only NAND gates, we will be using De Morgan's theorem. Now let us take one example in which we have been given one switching function, and based on the given switching function, we will be implementing logic circuit, but now with only NAND gates. So function given, that is A bar dot B bar plus A bar dot C bar plus ABC. So when we use NAND gate, one thing should be very clear, that it is applicable to SOP type of function. So sum of product, here we can see that we have three product terms, A bar dot B bar, A bar dot C bar, and A dot B dot C, and it is added with a plus sign. So it is a SOP type of function. It is not a standard SOP, but it should be SOP. So now we use one of the property of the Boolean algebra, that is F is equal to F double bar. When we invert and when we re-invert, it becomes original input. So F is equal to F double bar, both are equal. So first we write our original switching function, then we add double bar. The original switching function F remain as it is when we add double bar. Then we apply De Morgan's theorem. We apply De Morgan's theorem for this part as it is indicated. We leave this white bar as it is, and with the whole bar, that is blue, we'll apply De Morgan's theorem. Now we know that De Morgan's theorem says that complement of a sum, that is equal to product of complements. Now let us see how we can write after applying De Morgan's theorem. So we have original equation, but now it is converted into product, because in De Morgan's theorem it says that complement of a sum. So here we have a complement of sum, that is equal to product of complements. So now we have converted our original switching equation like this, and we have a whole bar white that we have to keep as it is. So this is now final converted Boolean expression or switching function from which we have to implement our logic circuit using only NAND gates. Now we write again our equation, switching function. Now we have to use only NAND gates. So let us check. See, for the A bar, we have to use one NAND gate. So first NAND gate we use for A bar. We only have ABC input, and to get A bar, B bar and C bar, we have to use a NAND gate as a NOT gate. Second NAND gate we use to prepare B bar, and same way for the C bar we have to use third NAND gate. Now we have three product terms. So for the first product term with complements, we use our fourth NAND gate. With another product term, we use fifth NAND gate. With the last product term, we use sixth NAND gate. Now all the product terms again multiplied together. So as a whole, we'll be using seventh NAND gate. So as per this Boolean function, we have to use total 7 NAND gates when we implement logic circuit using only NAND gates. Now let us implement our logic circuit. We have input A, input B, input C. We use a first NAND gate as a NOT gate, and then we have A bar. We use second NAND gate as a NOT gate, and we have B bar. Third NAND gate again as a NOT gate connected to C input, and we get C bar. So after using 3 NAND gates, we have 3 inputs available ABC. Now it is converted into A bar, B bar and C bar. Now we can use either ABC or A bar, B bar, C bar as an input to another NAND gate. Now we use fourth NAND gate. We give input A bar, B bar, then output, because we have given input A bar dot B bar and we are using NAND gate, so we get a whole bar. We use a fifth NAND gate. We give input A bar and C bar, so A bar dot C bar and the whole bar, because we use NAND gate. We use a sixth NAND gate. In sixth NAND gate we have 3 input, so we use NAND gate with the 3 input. We have 1 input A, B and C. We have 3 input, and we get A dot B dot C whole bar because we are using NAND gate. Now final NAND gate, that is our 7th NAND gate, and we have to take input of all the intermediate NAND gates, and we get output, that is our final output, and we use a NAND gate at the last stage, so we have a whole bar. So this is exactly the equation we have prepared after applying De Morgan's theorem. So this way we can implement our logic circuit using only NAND gates. Now let us take another example, then it will be very clear. Now we take one switching function, that is f is equal to A bar dot B dot C plus A dot B bar dot C. Again, in the given switching function we have 2 product terms and both the product terms are added together. So it is a SOP type of Boolean function, and we can implement with the only NAND gates. Let us use the property that indicates f is equal to f double bar. We know that when we apply double bar, the original value remain as it is. So we have our switching function A bar dot B dot C plus A dot B bar dot C, but now we apply double bar. Then we apply De Morgan's theorem. We leave white whole bar as it is, and with the blue bar we apply De Morgan's theorem. So when we apply De Morgan's theorem, we know that a complement of sum equals product of complements. So our function, after applying De Morgan's theorem, it is converted as a product of complements, and white whole bar we kept as it is. So this is our converted function which we are using for the implementation. So we write our function as it is. We know that one NAND gate we have to use for the A bar. Second NAND gate we have to use to get B bar. We use a third NAND gate for the product term, that is A bar dot B dot C whole bar. We use a fourth NAND gate for the another product term, and for the whole equation we use a last NAND gate, that is fifth NAND gate. So in this switching function we require only 5 NAND gates to implement the logic circuit using only NAND gates. Now let us implement our circuit. We have input A, input B and input C. We always have an input either ABC or whatever is required. All remaining part we have to get converted using NAND gate. In this equation we require A bar as well as B bar. So we use 2 NAND gates to get A bar and B bar. We do not require C bar, so we will not use any NAND gate to get C bar. We use a first NAND gate and we get A bar, second NAND gate to get B bar. Then we use a third NAND gate. In third NAND gate we have 3 inputs because product term is with the 3 literals. We use A bar, 1 input. Then we have B and C as a second and third input. So at the output of the NAND gate we get A bar dot B dot C, and because we use a NAND gate we have whole bar. Same way we use a fourth NAND gate, that is also with the 3 input. We use A 1 input, B bar and C. We have used again 3 input. So at the output we get A dot B bar dot C, and because we use the NAND gate we have whole bar. Now we use a fifth NAND gate, that is with the 2 input, and output of both the intermediate NAND gate we apply as an input to the fifth NAND gate, and that is the output as we require. We have 2 terms as an input to the final NAND gate, and that we get at the output, and because we use a NAND gate at the last stage we have to apply whole bar. So this is our final switching function implementation using only NAND gates. So we have to apply De Morgan's theorem. So NAND gate and De Morgan's theorem both should be very much clear. Then it will be very easy to implement any logic circuit either using NAND gate or using NOR gate only. In case of SOP function we use only NAND gate. In POS type of function we can apply only NOR gates. So thank you very much for watching my video. Keep watching. Thank you very much.